Um, um, so I'm Shu Kabe, and I'm going to present our work done jointly with Professor Alexander Fraser. We're both from the Technische Universität München, so in Germany. And this work is on bilingual sentence mining for low-resource languages. And we're going to do a case study on two languages which are endangered, which are Upper and Lower Sorbian. And before I talk more on the languages, I'm going to present the task itself. What is parallel sentence mining? To understand this, we have to present parallel sentences and parallel corpora. So here you have an example of a parallel corpus. You have an English sentence on the left and a German corresponding sentence, its translation in German. So you may recognize a very widely used corpus in NLP, which is the European Parliament corpus. And we have this for English-German as a language pair. You can also see that this is very valuable for NLP because it enables you to train other NLP models. For instance, machine translation. This is the most obvious use of parallel corpora because you have translation pairs. So this is very valuable and a very well sought kind of resource for language pairs. We have here an institutional parallel corpus, but there are also other sources for such parallel sentences. We can think of news media, for instance. So here you have some screenshots from two websites, the one from BBC for the United Kingdom and Deutsche Welle, which is from a German media outlet. And you have many languages that you can choose. So of course, not all articles in English, for instance, for BBC is translated into one of these languages, but some are, because when you have worldwide events or very relevant or important events happening, they're going to be translated. And then you may get such parallel sentences and parallel pairs. Another well-known source for parallel sentences is Wikipedia, which is also very used in NLP. And as you have already noticed, you have options to choose another language. We present this because sometimes you can notice that some paragraphs or sentences have been translated from another language. So for instance, for a German city, perhaps the English sentence comes from the German article on the same topic. In both of these two cases, there is, however, no guarantee that all the sentences have actual counterparts, actual translations in another article. This is why we care about parallel sentence mining, which is the task we are presenting. So the idea is basically finding parallel sentences from two monolingual corpora. So let's say you have an English corpus with a lot of sentences, another one in German. The idea is to find the corresponding translation pairs. Here we have I to an apple and its translation in German here. You can also see that there is one main challenge, which is that not all sentences have a counterpart in the other corpus. For instance, this English sentence may not have a translation in the other one. The second main challenge that exists for this task is the distance between the two languages. So here we choose English and German for the sake of to present this task. But if you have English and another language, especially a low resource language, it's going to be even more difficult. So how do we actually do this kind of parallel sentence mining? Well, we're going to represent words and then sentences as vectors. And as you have probably already seen this kind of figure from 2013, what we do is to convert these words into vectors. So we have these kind of representations, and we can get good properties if the representation is well conceived, such as here the relationship between countries and capital cities. But we can extend these word embeddings or word representations to that sentence level and represent a full sentence as one vector. And this is what you can see in the figure on the right. Again, if the representation is correct or good, you will have some properties in the vector space, in the representation space, such as similar sentences being somewhat close. So we see it here in this example with I eat an apple and I eat a pear, which are both involving eating a fruit. They're closer compared to other sentences. So in the previous example here, I presented the pair of English-German. And this is a language pair which is quite well resourced. So individually, so English and German are well-resourced, and the language pair itself, English-German, is well-resourced, for instance, with the European Parliament corpus I showed in the beginning. But what happens when we change one of the language for low-resource languages, or more importantly, with an endangered language? And this is what we've done here with a case study on Sorbian languages. So a few words, of course, on both Sorbian languages. So there are two minority languages spoken in Germany, and you have Upper Sorbian here, which is spoken in Saxony, and it's closer to Czech in terms of language. And you have here Lower Sorbian, which is spoken in Brandenburg, and it's closer to Polish. And of course, I mean, the closest language is, they're mutually the closest language, so Upper Sorbian is the closest to Lower Sorbian, and conversely. So there are two West Slavic languages, which means that they're a bit further, they're from another language branch than German, which is from the German language family. And as you can imagine, there are needs for this kind of language pair, German paired with one of the Sorbian language, because there are two endangered languages, and there are some needs for these translations or language pairs. So another reason why we focus on this, the two language pairs, is because of the previous collaborations that existed between our research group and two nonprofits that are working on both Sorbian languages. So there are the Vidai Sprachzentrum, which is the Vidai Language Center, and the Sorbian Institute. They both collaborated with our research group for three shared tasks on machine translation during the WMT conference or workshop on machine translation for unsupervised and very low resource languages. Thanks to these previous collaboration, we actually have parallel sentences and parallel corpora. So we have the actual true pairings of sentences. So what we have done here in our work is to inject these kinds of parallel sentences to the monolingual corpus, randomly, of course. So we have a German text, we inject the German side of the parallel sentences, and in the Upper Sorbian monolingual corpus, we inject the Upper Sorbian side of the parallel sentences. Then, as you can guess, the idea is to find back these pairs, so that we have originally, and of course, there will be other sentences that will not be matched. With this kind of a methodology, we now have a controlled data set for which we know the true pairings of parallel sentences, and we have a somewhat realistic scenario of what we can have if we want to carry out parallel sentence mining in a real condition. So if you have two monolingual, for instance, Wikipedia articles, you can reproduce this kind of scenario and find the parallel sentences. Now, when it comes to the mining pipeline, we have here a very brief overview of it. So the input is, of course, the monolingual sentence in German or in Sorbian, one of the Sorbian languages. It's going to go through a multilingual language model to represent it into a sentence representation space. And here we're going to use a multilingual language model, and the same one, which will enable us to represent both German sentences and Sorbian sentences in the same space. Since they're both in the same space, we can actually then compute the similarity scores between sentences, so between a German sentence and a Sorbian sentence. Once we compute the similarity scores between several pairs, possible pairs, we can then filter the sentences according to the similarity and only keep sentence pairs for which there is a high similarity score or high enough. And this will give us our mined parallel corpus. So the key thing in our pipeline is this multilingual language models. We focused on two baseline models, which are very popular. The first one is, of course, XLMR, which has been used widely for many LLMP tasks. And the second one is GLOT 500M, which is a kind of extension of XLMR to low resource languages and more. And this is about more than 500. It's like 511 languages that are covered by the language model, which is way higher than the 100 covered by XLMR. So of course, both language models have seen Czech and Polish, which are the closest West Slavic languages for both Sorbian languages. Glot500M has actually seen some Upper Sorbian sentences, and XLMR hasn't. And for Lower Sorbian, neither of the models have seen sentences in that language. And this is also very interesting in the sense that we can now compare the impact of having seen sentences in Upper Sorbian by comparing XLMR's performance and Glot500M, and also see how well knowledge of Upper Sorbian can help mining Lower Sorbian sentences. We have also carried out some pre-training of language models. So we have taken XLMR and given increasing amounts or numbers of sentences in Upper Sorbian. So we have 30, 60, and 90,000 sentences in Upper Sorbian that are given to XLMR in order to improve the model and hope that it improves the mining quality. And additionally, we have also given a very large amount of parallel sentences in German and Czech, which is the closest, better resourced language for Upper Sorbian. And we have given more than 200,000 sentences. And this gives us the following results that you see here. We represent the F-score, which tells us how good the mined parallel corpus is. So the higher, the better. And we have our 6 models that we're going to compare, the 2 baselines, so XLMR, Glot500M, and the 4 pre-trained models that I just presented. If we just focus on the baseline models, so we have XLMR and Glot500M, we see that having seen Upper Sorbian sentences during pre-training is actually a very crucial component in improving the mining quality, as you see here, with a very significantly higher score for Glot500M compared to XLMR. This also shows that having seen only Czech or Polish is not enough to mine Upper Sorbian sentences. So the representation of the language is not usable for mining, for the mining task. When we look at the pre-trained models, you can see that starting from 60,000 sentences, we start to reach a kind of stagnating performance in the mining quality. And using these parallel sentences in a large scale, so adding 200,000 Czech and German parallel sentences is going to give us a boost. So this was for Upper Sorbian. We then used the same models, but on another data set, on the Lower Sorbian data set. And you see this kind of results. I changed the scale for better visibility. So this is significantly lower than what you see on the left. But overall, you can see that the F-scores are far lower for all models, even though they follow somewhat the same kind of trend, they're very low. So this suggests that having seen no Lower Sorbian sentences at all is going to be a huge issue when you do mining, sentence mining, which can be somewhat expected, but here you have kind of evidence of this. More generally, you can also see that the best performing model on the left has only an F-score of 30, which is somewhat low. So what we have done is a kind of post-processing of the mined corpus. So we do the full mining pipeline, and we have our mined corpus, and then we're going to go through this mined corpus and filter out sentence pairs which are not highly aligned. And to do so, we use an unsupervised aligner. The intuition is, as you see here in this example, when you have a real parallel sentence, so translations of each other, you will be able to draw alignment links between each words of the sentence pair, which is here. I eat an apple, and its German translation, we can draw links between each of the words. So we have a high alignment score, 100%. Whereas if you have a sentence pair for which there is not enough alignments because they're not true translations, such as here in this example, we have the same I eat an apple in German, but in English we have I take a bus. There will be words for which we will not have any alignments, such as bus and take, for which in this case we have a lower alignment score. Based on this, we're going to be able to filter out some sentence pairs which are of high or low quality. Doing this post-processing, we managed to have a significant increase in the mining task or mined corpus as we go from 30 from the best performing approach so far to 50. I will present some examples of what we have mined. So here is an Upper Sorbian sentence, and this is the German sentence. It has been paired with XLMR, which was the poorest performing model. And this is with the best performing model. You have this. If you look at the translations, they have nothing to do in terms of topic. And the true translation is, of course, the one which has been found by the best model, which talks about moderated discussion and not about leaves of trees. This also shows that XLMR's representation of Upper Sorbian is very poor because it has not seen any sentences and words in that language. But there is, however, some limitations in our current approach, and this is one of the, let's say, pattern that we see in the errors. We have an Upper Sorbian sentence and a German sentence. I didn't put the translations, but we can focus on the colored parts. So in red in Upper Sorbian, we have Sunday the 15th of July, and in German, we have Wednesday the 9th of December, and we have 5 p.m. in Upper Sorbian and 8 p.m., let's say, in German. So they're not translations, but are considered to be parallel by our mining pipeline and post-processing. So why is that? It's because both sentences talk about similar topics. They both talk about a show that is going to air at some point, and they follow some kind of structure also. So there's the show and the date and time. And if you recall the example about I eat a pear and an apple, when you have similar sentences, but not actually translations, but like similar sentences, they're going to be close in the representation space. And these two sentences are somewhat close, which is why they have been considered to be parallel, although they're not. This leads me to my conclusion. So we have done parallel sentence mining for two language pairs, German paired with Upper or Lower Sorbian, and both languages are endangered languages. Although they benefit from institutional support and non-profit support, they're still endangered, and there is actual need for this language pair, which is German paired with one of the Sorbian languages. We have focused on this parallel sentence mining task because it enables us to create a parallel corpus that can then be used for other NLP tools. The most straightforward application is for machine translation, but this is for afterwards. We have carried out this mining pipeline using multilingual language models, and we have seen how having seen or not seen sentences in the language impacts the mining quality. And we have seen that relying only on related languages is not enough to have good mining quality, and that's what we have seen with Lower Sorbian especially. We have also carried out an alignment post-processing in order to improve the mining quality based on word level alignments, and it's an unsupervised model. And finally, we release the data, so this benchmark data that we created by injecting parallel sentences. And also the mining tool is released under this link. And I will also use this opportunity to say a few words on our current work, basically. So the work I presented today is part of the ERC Proof of Concept grant, where we try to create tools for language activists and language communities directly. And we have organized last month, actually, an online workshop where we presented, it was the first workshop, we presented NLP tools that can be possible to use for language communities. And there is, of course, a large variety from language with very limited digital presence to language for which there are more sentences, as we see here with the Sorbian languages. After this workshop, we have some ongoing collaboration in order to extend this parallel sentence mining tool to other languages when there is need. And also we're talking about other tools, depending on what kind of data, or what kind of tools, or what kind of needs each community have. And if you're interested in just following our work, or if you have some questions, you can also join our Google group that you have here in the QR code. So far, we're focusing on the parallel sentence mining task, which means that you need to have written text, which is not the case for all endangered languages, of course. But this is one initial step that we have carried out. By focusing and doing this case study on Sorbian languages, the German upper and lower Sorbian sentences, we have seen a kind of upper bound of performance that we can reach because there is data, we have the parallel sentences, and we can see how well we can go with the current NLP model tools. So thank you very much for your attention, and I'm happy to answer any questions. Thank you.
Thank you for your talk. I was curious about the step you did with the post-processing. I was wondering what the minimum alignment percentage that you had to be required to make it through the filter was, and like how you guys settled on that like ratio.
I'm sorry, I think I didn't hear everything.
So I was wondering about the
Post-processing?
Yeah, so the post-processing, you say that there needed to be a certain alignment score to make it past the filter. What was that score, and how did you come up with that benchmark?
So yes, we use this alignment post-processing. So we run this word aligner, which is unsupervised, and we then get, as you can imagine, for each sentence pair, different alignment scores. So let's say 100, 80, and so on. We then compute the distribution of all of these scores and filter out, depending on the distribution. We have also, so I didn't mention this, but we have a training and much larger test data set. We find the best alignment score on a small training data set, and then we apply it on the test data set. This is what we've done. This follows one of the methodology that existed for this parallel sentence mining task. I hope it answered your question.
Yes, thank you.
Okay.
So I had a question, and I think you may have partly answered it, but I've heard and seen things where in machine translation with low resource language, it's one thing they work on is first aligning like proper names or dealing with them because they're easy to align and they do mess up things like you showed in your example with the dates. Have you tried, or are you thinking about applying anything like name to T recognition first to kind of take those things out? Do you think that would help the quality if you did some sort of
so that's so that's a good point. So as we presented here, we have issues with, for instance, days, times, and of course also names of people, because since there are names, they're going to be closely represented in the space, and we have these kind of issues. We have actually thought of doing a kind of projection. The thing is, for German, for instance, for the well-resourced language pair, we have easy named entity recognition, but for the upper Sorbian sentences, we do not yet have good, I think we don't even have like labeled data for upper Sorbian. So I think we also will need to do some kind of tools for this, but that's a path that we're still considering because of these kinds of errors that we showed, like very similar sentences, but it's very clear that it's not like translations because they're key components that are not translations.
Any other questions in the audience? Okay, and no questions online, I think. All right, well.
Thank you.
So we've got about 5 minutes. We'll try to stay on time for our last presentation for people who might be coming online just for that presentation. So we've got 2-3 minute break and we'll set up maybe this time without causing delays. So is our next speaker ready? You ready there? You want to try just like sharing your screen and we can test the audio.